Good morning, everyone. It feels like we're kicking off the joint mathematics meetings. I'm Boris Hasselblatt, Secretary of the AMS, and it's a great pleasure to welcome you all to Seattle. I also look forward to seeing you again in this very room at 4:30 p.m. for the official opening of the joint mathematics meetings. Right now, it's my privilege to welcome you to the von Neumann lecture, through which the American Mathematical Society honors the mathematical legacy of John von Neumann. A little bit about him. John von Neumann was born in 1903, and when he finished high school, he was already recognized as a professional mathematician. He simultaneously studied mathematics at the University of Budapest and chemical engineering at the Swiss Federal Institute of Technology, receiving his mathematics doctorate and chemical engineering diploma at the same time. In the 1920s, he held faculty positions in Berlin and Hamburg, and in 1930, he came to the US. The rest is history. He's one of the giants of the 20th century, and I recommend reading up on him after this lecture. This year's von Neumann lecturer is Lester Mackey, the principal researcher at Microsoft Research with a faculty appointment at Stanford University. One should not use the word genius lightly, but in this case we're looking at a 2023 MacArthur Fellow, so the temptation is great. Indeed, Lester has made major contributions to all aspects of statistics and machine learning. He has done deep theoretical work on the mathematical foundations of the subject, as illustrated by his talk today on Stein's method, learning, and inference. But what actually drives him is a problem where mathematics can be applied or for which new mathematics can be developed. He has done important practical work on real-world problems, ranging from predicting disease progression in ALS patients and work on cancer immunotherapy to sub-seasonal climate forecasting aimed at guiding agriculture, allocating water, mitigating fires, droughts, and floods. In each case, there's promise that the new methods will transcend their original purpose. He has also thought deeply about the philosophical question of what we should be working on and why. And he's a prominent proponent of statistics for social good. The net effect is that he has a unique vision and exceptionally broad perspective. It's a great privilege to yield the podium to him.
Good morning, everybody, and thank you for having me here. It's a great privilege to be here. My talk is about three things: learning, inference, and Stein's method. Now, I imagine that most of you have heard of machine learning, and I imagine that many have heard of probabilistic inference, but perhaps many fewer have heard of Stein's method. That's okay. By the end of this talk, you'll know much more about this somewhat obscure tool from probability theory, and I hope that you'll come away with an appreciation for its utility for solving practical problems in learning and inference. Our first motivating problem is that of large-scale posterior inference. And to illustrate what I mean by that, I'd like you to consider the classical setting of logistic regression. In logistic regression, you have a data set. Each data set has a data point. It's a vector in RD. There are L data points all together. And each data point also has a label, a class label which is either 0 or 1. Now, the labels are related to the feature vectors via an unknown parameter vector, let's call it beta, also an R to the D. And this parameter vector parametrizes the likelihood of those class labels. Now, beta is unknown, so we could put a prior distribution on that beta, representing our uncertainty about it. So a typical prior distribution might be this standard Gaussian distribution on each component. Okay, what I want to highlight about this generative model is that it's pretty simple to express. But at the same time, the posterior distribution, that is the conditional distribution of the parameters given the data, is already complex. In this case, the normalization constant of that distribution is unknown, and exact integration under that posterior distribution is already intractable. So what do we do in a situation like this? Well, a standard inferential approach is to use Markov chain Monte Carlo, MCMC for short, to eventually draw samples from that posterior distribution. And the benefit is that we can now approximate these intractable integrals under our posterior, P here represents our posterior distribution, with asymptotically exact sample estimates just by averaging across the iterates of that Markov chain that I ran. But there's also a problem, and the problem is that each new sample point from your Markov chain requires iterating over the entire observed data set, and this quickly becomes prohibitive when your data set is large. So what do we do? How do we scale MCMC posterior inference to these massive data sets? Well, over the past decade, a template solution has arisen, which is approximate MCMC with subset posteriors. The basic idea is that instead of running an exact Markov chain, I'll approximate it in a way that only uses a subset of the data to draw each new sample point. And the idea is that this will lead to reduced computational overhead and hence faster sampling, which means I can reduce my overall Monte Carlo variance when I'm estimating integrals. But it also introduces an asymptotic bias. The target distribution of this approximate chain is no longer the stationary. The target distribution is no longer the stationary distribution of this approximate chain. But the hope is that for a fixed amount of sampling time, the variance reduction will outweigh the bias that's introduced. Okay, so this seems like a promising path to me and to many others, but it introduces a number of new challenges. In particular, how do we compare and evaluate samples that are being generated by these approximate MCMC procedures? And how do we select amongst different candidate samplers, and how do we choose their tuning parameters in practice? And finally, how do we quantify this bias variance trade-off that I just alluded to? Well, the difficulty is that while there are standard evaluation criteria for Markov chain Monte Carlo, these criteria, like effective sample size, trace plots, and variance diagnostics, all assume eventual convergence to the target distribution. This means that they're not accounting for that asymptotic bias. So in this talk, I'm going to introduce some new quality measures that are actually suitable for comparing the quality of these approximate MCMC samples. Okay, we're going to be even more ambitious. What we want to do now is to develop a quality measure, suitable for comparing the quality of any two samples that are approximating a common target distribution. Now here's our setup. We'll be working with continuous target distributions P. For today, I'll say the support is all of R to the D, and it will have a density, a Lebesgue density, little p. And we'll know little p up to its normalization constant, but we'll assume that integration under P is intractable for most functions of interest. Okay, so how are we going to approximate P? Well, we're going to approximate it with a series of sample points, x1 through xn. Together, these points define a discrete distribution, which we'll call Qn, and they allow us to approximate integrals under P using just a simple sample average under Qn. Now, I'm not going to make any particular assumptions about the provenance of these points. So they could be coming from MCMC, but they could also be coming from any other sampling or even deterministic quadrature rule. All we want from Qn is all we want to know about Qn is how well it approximates integration under P. And we want to do this in a manner that satisfies a few desiderata. First, our tool should be able to detect when a sample sequence is converging to the target. It should also be able to detect when a sample sequence is not converging to the target. And finally, it should be computationally feasible so we can actually use it in practice. Okay, so given that our goal is to quantify how well sample expectations approximate target expectations, we're going to be considering integral probability metrics, or IPMs for short. IPMs literally measure the maximum discrepancy in sample and target expectations over a class of test functions. And when this class is sufficiently large, it will control convergence, meaning that if your IPM converges to 0, you're guaranteed that your sample sequence is converging to P, satisfying our second requirement. The problem is that while there are many familiar IPMs out there, like the 1 Wasserstein distance, most IPMs can't actually be computed in practice. Why is this? Well, we don't know how to integrate under P. And the definition of an IPM involves explicit integration under P. This is a problem for us. But here's an idea. What if we only considered test functions that we knew a priori were mean zero under the target distribution? If we could do that, then this EP term would disappear, and our quality measure would only depend on the sample. And we know how to take sample expectations, those are just averages. So this is potentially something that we could compute. So it seems like a reasonable idea, but it raises some additional questions, like how do you pick these mean zero test functions? And will the resulting discrepancy measure track convergence and non-convergence in the way we want it to? And finally, how do we solve the resulting optimization problem, which is still an infinite dimensional optimization problem over a function space? So we'll come back to the third question in a bit, but first I want to show you how we can address the first two questions using ideas from Stein's method. Stein's method is a tool developed in the 1970s by Charles Stein, and it provides a recipe for controlling convergence. I like to think of it as a three-step recipe. The first step is to identify an operator, we'll call it T, and a set, G, that together generate mean zero functions under your target distribution. Okay, the operator T, we'll call it a Stein operator, we'll call G a Stein set, and G is a set of functions. They're going to be vector-valued functions in this talk. You pass your functions through your operator, and what's outputted is a scalar function that's mean zero under P. Together, the operator and the set define what we'll call a Stein discrepancy. This is an integral probability metric type measure that has no explicit integration under P because all the functions are mean zero by design. Okay, we'll call that S, and it takes in your sample Qn, your operator T, and your set G. Okay, now you have a discrepancy measure you can compute, but we don't know anything about it. So the second step is to lower bound that Stein discrepancy by a reference IPM that you know and trust, like the Wasserstein distance. This would mean that whenever your Stein discrepancy goes to zero, your reference IPM also goes to zero, and you're controlling convergence, that is, detecting when a sequence is not converging in the way that you like to. Typically, this involves intensive analysis, but that can be performed once in advance for large classes of target distributions, and then you can go off and happily use your Stein discrepancy, knowing that it has this property. Finally, the third step is to upper bound the Stein discrepancy by any means necessary to show that it converges to zero when your sample sequence is converging to P. This step will actually be the least important for us because in practice, we're just going to compute the Stein discrepancy and we'll see how big it is. But it's still nice to know that you have this property, and we'll talk about that today as well. Now, the standard use of this recipe is as an analytical tool to prove convergence in distribution and to prove rates of convergence. But today, I'd like to adapt it to develop a Stein discrepancy into a practical quality measure that we can use in practice when assessing MCMC algorithms. Okay, so before we turn to the practicalities, let me give you a specific instantiation of this otherwise very abstract recipe. So first, step one, identify a Stein operator T. We want to find an operator that generates mean zero functions under P. To do this, we're going to appeal to this beautiful idea due to Andrew Barbour called the generator method. And the idea is that if you can identify a Markov process that has P as its stationary distribution, then under very mild conditions, its infinitesimal generator generates mean zero functions under P. Now, I've given you the definition of an infinitesimal generator here. Fortunately, you don't need to remember that. We're really just going to focus on one process and one specific generator, which I've detailed here. We're going to focus on what's called the overdamped Langevin diffusion. The generator of the Langevin diffusion has this form, and the Stein operator that we're going to use is this function here, Tp. I want to highlight a couple of things about this operator. First, it only depends on P through the gradient of its log density. This is great for us because it means that even if you don't know the normalization constant, you can still potentially compute this thing. Second, when your functions are sufficiently bounded and have bounded derivatives, this operator will generate mean zero functions under the target distribution. So in particular, if the functions belong to what we'll call the classical Stein set, which just says that the functions are bounded, have bounded derivatives, and one Lipschitz derivatives, then all outputs of this operator will be mean zero as desired. So together, this Langevin-Stein operator and this classical Stein set will give us what I'll call a classical Stein discrepancy. Okay, so first, we need to check what are the properties of this Stein discrepancy. Does it detect convergence and non-convergence in the way we like it to? In other words, we'd like to show that the classical Stein discrepancy goes to zero if and only if your sample sequence is converging to P. Now, it turns out that in the univariate case, when d equals 1, it's known that for many targets, the Stein discrepancy goes to zero if and only if the one Wasserstein distance goes to zero. But relatively few multivariate targets have been studied. Though I think the one major exception is the multivariate Gaussian, another is the Dirichlet distribution. So to expand the reach of this literature, my colleagues and I established the following result, which says that if the Langevin diffusion underlying that operator mixes quickly and the score function, grad log p, is Lipschitz, then your Stein discrepancy goes to zero if and only if your Wasserstein distance goes to zero. And this covers lots of multivariate distributions. It covers all strongly log concave distributions. It covers the Bayesian logistic regression with Gaussian priors that I mentioned earlier. But actually also covers non-log concave distributions like robust students T regression with Gaussian priors and even Gaussian mixtures which have multiple modes. I also want to highlight that the conditions of this theorem are not necessary, but we're hoping that others can use it as a template for bounding Stein discrepancies for other large classes of distributions. So this is great. This satisfies our first two requirements. And it turns out that a small modification of this classical Stein discrepancy is also computable just by solving a linear program. So I'm going to now show you how to use it in practice. And I want to start with a very simple example just to highlight some basic properties of the Stein discrepancy. So here I have two different sample sequences. The sequence in red is an IID sequence from a standard normal. Our target is a standard normal, and I'm sampling IID from that standard normal. In teal, I have an IID sequence not from the target. It's from a student's T with matching mean and variance, but otherwise it's a different distribution. Now, as I collect more and more sample points, I should see that my red sequence is converging to P, and my teal sequence stays bounded away from P, because one is indeed converging distribution and the other is not. And that's what we're seeing here. The on-target sequence in red is converging at basically a 1 over square root n rate, which is what you would expect in this case. And the off-target sequence in teal remains bounded away for all sufficiently large sample sizes. So that's great. But on top of actually being able to compute the value of the Stein discrepancy, it turns out that you can also recover the function that optimize that integral probability metric. That's the function g here. But even more interesting than that function is the function passed through the Stein operator, because that's the test function that should have been mean zero under P that was farthest from being mean zero under your sample. So for instance, in the student's T case, this worst case function has a lot of mass in the tails where the student's T is heavily oversampled relative to a Gaussian. So it gives you some diagnostic information about which ways your sample is not approximating the target. Okay, now here's a more interesting example using posterior inference. In this case, our target distribution P is the product of a prior, pi, and a series of likelihood terms, one for each data point that we've observed. And we're going to use one of these approximate MC procedures that I mentioned, one of the most famous ones, which is called stochastic gradient Langevin dynamics. How does this work? Well, for every new sample point, to generate a new sample point, you start at your last point, and you'd like to take a step in the gradient direction of the target distribution. But it's expensive to compute grad log p because there are so many data point terms. So instead of that, you just subsample a few of them, and you use a stochastic gradient as an approximation of that gradient. Then you add some Gaussian noise. And normally, if you wanted a chain that was guaranteed to mix to the target, you consider this to be a proposal and then you'd correct it using something like Metropolis Hastings. But it turns out Metropolis Hastings is expensive. So instead, stochastic gradient Langevin dynamics just throws away the correction step and hopes for the best. As you might imagine, throwing away the correction step leads to some problems, or it could. And it means that the step size that you take in this algorithm has a big impact on the quality of your sample. So if your step size is too small, that means you have very slow mixing. So after taking 1,000 samples, after generating 1,000 sample points as I have here, you see that I've barely left the starting point of my Markov chain. On the other hand, if you choose your step size too large, you'll mix quite quickly, but you'll be mixing to the wrong distribution. Because the larger epsilon is, the farther you are from the correct distribution. And so you introduce substantial bias, and you end up with a distribution that looks like this. Now, in this triptych here, the contours I've drawn are the equidensity contours of the target distribution. So ideally, you'd want your sample to look like those contours. And here you can see that the sample is greatly underdispersed, and here it's greatly overdispersed. So how do you pick the sample size? How do you pick the step size in practice? Well, there are standard diagnostics out there. One of the most common is called effective sample size, which is essentially a measure of autocorrelation. And so if you were to apply effective sample size in this case, if we were to generate different Markov chains with different step sizes and evaluate them according to effective sample size, ESS would say, pick the one with the largest sample size because the points are the least autocorrelated. They look like they're mixing most quickly, and indeed they are, but this diagnostic doesn't account for bias. So it doesn't know that this is actually just sampling quickly from the wrong distribution. Meanwhile, if you use the Stein discrepancy that I described to evaluate each sample size, it will say, well, when your step size is too small, you're getting a bad approximation. Smaller is better here. When your step size is too large, you're getting a bad approximation. And somewhere in between, you're getting the best. In this case, it picks out the step size in the middle, which indeed offers the best approximation to our target. Okay, so I mentioned briefly that the way we were computing the Stein discrepancy was by solving a linear program. And that does work, but you might imagine having something a bit more user-friendly. So our goal now is to identify a different Stein set than the classical one that leads to more user-friendly computation. And to do this, we're going to appeal to this beautiful idea due to Oates, Girolami, and Chopin of mean zero reproducing kernels. Now, a reproducing kernel is a function of two arguments that's symmetric in those two arguments, and that's positive semi-definite in the sense that if you formed a matrix of pairwise evaluations of this function, then that matrix is always a positive semi-definite matrix. Two common examples are the Gaussian kernel, which looks just like a Gaussian density evaluated at x minus y, and an IMQ kernel, or inverse multi-quadratic kernel, that's like a Gaussian kernel except it has polynomial decay. What we need from this kernel is that it generates what's called a reproducing kernel Hilbert space. And in particular, this is going to allow us to define a new sort of Stein set, where each component of our function, remember G is a vector-valued function, each component belongs to that reproducing kernel Hilbert space, I'll call it RKHS for short, and they're jointly bounded in that space. Their norms are jointly bounded in that space. Why do we like this set? Well, it turns out that this Stein set yields closed-form kernel Stein discrepancies. That is, we can exactly evaluate that infinite dimensional optimization problem over the unit ball, and this is how you do it. You take an input kernel K, I'll call that the base kernel, and you form a new kernel that's mean zero under your target. And essentially you do that just by applying the Stein operator to each argument of your kernel. I've written it compactly here, but if you work out the algebra, you can see that this is actually just depends on P through the gradient of its log density as before. Once you have these Stein kernels, all you need to do is just evaluate it at each pair of sample points, sum up those evaluations, and that gives you your Stein discrepancy. So that's pretty simple and even parallelizable across those evaluations. Okay, but does it have good detection properties? In particular, does it detect non-convergence in the way we'd like it to? Well, here's a theorem, and this theorem says that in the univariate case, indeed, KSDs do detect non-convergence. It says if you use a standard translation invariant kernel that's in C2 with several properties that don't matter that much for this talk, then whenever your Stein discrepancy goes to 0, you know that your sample sequence was converging to 0. Now this is for a class of target distributions, and it's essentially the same class of target distributions that we considered before. Those with strongly log concave tails and Lipschitz score functions, Lipschitz grad log p. So this includes the Bayesian logistic regression, student's T regression with Gaussian priors. It even includes Gaussian mixtures. So these distributions need not be strongly log concave, but they have strongly log concave tails. So this actually justifies the use of the KSD for lots of standard kernels, including the Gaussian and IMQ kernels that I mentioned earlier, but only in the univariate case. So a natural question is, what happens in the multivariate case, which is actually the case we care most about? Well, it turns out that in higher dimensions, something odd happens. These same KSDs with these same kernels fail to detect non-convergence, even for very simple target distributions like the Gaussian. Here's a theorem about that, and it says whenever your dimension is 3 or greater, if your kernel decays too quickly, then it will fail to detect non-convergence for a Gaussian. And in particular, I could give you an explicit sample sequence that will drive your KSD to 0, even though it's not converging to a Gaussian or any other probability measure. So this basically rules out the Gaussian kernel, another exponentially decaying kernel called a return. It even rules out inverse multi-quadrant kernels if they're decaying too quickly. And the central problem is that these kernels that decay quickly, the kernels with light tails, ignore excess mass in the tails. So they don't control tightness. And just to give you an example to show you that this is indeed a problem in practice, here are 3 examples where my target distribution is standard normal in D dimensions. D is either 5, 8, or 20. And on the left, I'm just generating samples IID from the target and evaluating them with a kernel Stein discrepancy. And in each case, you see that the kernel Stein discrepancy is decaying to 0 as it should be. On the right, however, I'm constructing an off-target sequence that does not converge to P. This off-target sequence essentially just places a bunch of points on a ball and grows the radius of that ball at a certain rate, and it still drives your KSD to 0. That's a problem because you'd like to know if your sample sequence actually is converging. Now this happens for the Gaussian kernel, and it happens for the Matern kernel, but it turns out it's not happening for the inverse multi-quadrant kernel when its decay is very shallow, when its decay is very slowly, I should say. So this points to a potential hope. Maybe if we use a heavier tailed kernel, we can get around this convergence problem. And indeed, that's true. It turns out that whenever you use an inverse multi-quadrant kernel that decays slowly enough, then you're back to detecting convergence just as before in any dimension. And this holds not just for the Gaussian, but for all those target distributions that we discussed previously. Okay, so that's detecting non-convergence. That's probably the most important property. But we should also say something about detecting convergence. That is, if my sample sequence is going to 0, will my Stein discrepancy go to 0? And it turns out that this happens in broad generality for basically any kernel you could choose under pretty weak conditions. So if your kernel is sufficiently smooth, has a couple of bounded continuous derivatives, if your grad log p is Lipschitz and square integrable, then your Stein discrepancy will go to 0 whenever the Wasserstein distance goes to 0 as well. Okay, great. So now we have a tool that's easy to compute, controls convergence. Let's try it out on a problem. And we're going to assess another one of these approximate MCMC procedures designed for scalability. This one's called stochastic gradient Fisher scoring, or SGFS for short. There are 2 different versions of it, one that involves inverting a D by D matrix on every step, and one that doesn't. And so we're going to compare the 2 and see if the speed benefits outweigh the loss in quality. Here, our problem is going to be a 51-dimensional Bayesian logistic regression problem where the data actually comes from images. Okay, on the left, I'm showing you a comparison of these 2 procedures using the IMQ kernel Stein discrepancy. On top, we have the version that does not do a full inversion. On the bottom, we have the version that does a full inversion. And you can see from this plot that it seems like the full version is much better. That is, The KSD is smaller, and that's good. Smaller is better. But you might say to me, well, that's just a plot with some random discrepancy that you just introduced a slide ago. Why should I trust that? So on the right-hand side, I'm showing you a second evaluation of the same samples. In this case, I used a second auxiliary chain, a gold standard chain, to approximate the target distribution. And I ran it for a long time. It's Hamiltonian Monte Carlo. And I used that to assess the quality of these samples. And what you see here, what I'm showing you here is the best alignment between means and covariances across all pairwise marginals of the distributions. Remember, this is a 51-dimensional distribution. I can't show you a great plot of that in 51 dimensions, but I'm looking at pairwise marginals. And what you see basically is that the diagonal version, the one that doesn't do a full inversion, even in the best case, it's giving you a very poor approximation of the covariance. And the full version, even in the worst case, is giving you a rather good approximation of the covariance. So this assessment on the right coheres with the assessment on the left. But the drawback of the assessment on the right is that you need an auxiliary chain just to check this. Whereas on the left, you can just draw your samples from your approximate procedure and directly compare it to the target distribution. Okay, now we've been using these approximate MCMC procedures, and part of the reason why we're using them is because computing grad log p is expensive. But we are using grad log p in the Stein discrepancy. So you might ask, what if grad log p is too expensive to evaluate? So here's an example where that might occur. You're using a posterior density. It involves one term for every data point. That means every evaluation scales linearly with your data set size. So one potential solution is to subsample, much like you do inside of the approximate MCMC procedures. What we're going to do is replace the exact gradient evaluation with a stochastic gradient evaluation that just uses a random mini batch of data points. And it turns out that these resulting sub-stochastic Stein discrepancies, if you just plug in that as stochastic approximation, still inherit the convergence control properties of standard Stein discrepancies with probability 1. So that's great, because it means that in these same sorts of examples, like the one I showed you in the last slide, you can, instead of evaluating exact likelihoods, you can evaluate approximate likelihoods. Here I've shown you the same sort of comparison, where the red curves involve the exact gradient, and the blue curve involves only using 100 data points per gradient evaluation, so 100 times fewer computational cost. And you can see that the conclusions we would draw are exactly the same. We still prefer the F version over the D version. Okay, now so far I've also been focused mostly on sample quality comparison, for example, comparing samples from different samplers. But there are other tasks you can tackle with these same sorts of tools. Another that was proposed as an application by Chiwyal-Kowski et al. And by Liu et al. Is goodness of fit testing. And they suggested that you could use the KSD as a test statistic in a goodness of fit test to test whether your sample was actually drawn from a target distribution P. Now, in their experiments, they found that using a default Gaussian kernel experienced a considerable loss of power as the dimension D increased. So we're going to recreate their experiment with this IMQ kernel instead, since we know it has better convergence control properties. So here's the setup of their experiment. You have 500 data points. Your target is standard Gaussian in R to the D. But your data actually is a spiked standard Gaussian. So sample Gaussian plus a uniform on one component. And your goal is to be able to detect that this is indeed not a Gaussian draw. Here we're comparing 3 tests. There is the Gaussian KSD test in red, the IMQ KSD test in blue, and a classical test due to Baringhaus and Henze for Gaussianity in black. Now what you see is that all the tests work well for small dimensions. They all have full power for detecting this departure from Gaussianity. But the Gaussian test in particular starts to break down in higher dimensions and has almost no power by the time you get to 25 dimensions. There, the classical test also starts to break down in power. But if you just make this simple substitution, plugging in this IMQ kernel that we know converges, that we know controls convergence, over the Gaussian kernel that we know doesn't, that leads to full power across the range of the experiment. Okay, now you could also imagine using the KSD to improve sample quality. Someone hands you a sample, that's meant to approximate p, can you give me back another approximation that's even better? This was the idea in a paper by Liu and Li, and the idea was we'll fix the sample points and we'll optimize the weights of those sample points to minimize the KSD, that is, minimize a measure, the discrepancy measure directly to p. They again did this with a Gaussian kernel, and I'm going to recreate their experiment with one of these IMQ kernels. So here I'm showing you the mean sample approximation error, where our target is just an IID Gaussian as well. Again, your initial sample, target is a standard Gaussian in d dimensions. Your initial sample is just IID from that distribution. And now you're just improving the distribution by optimizing the weights. So in red, you see the quality when you don't optimize the weights. In green, you see the quality improvement when you optimize using the Gaussian kernel. And you're seeing significant improvements all the way up through dimension 100. And then if you optimize with the IMQ kernel instead, you get even more improvement. So this is a good way to improve the quality of your approximations. Okay, now you might imagine another task, which is generating de novo samples from a target distribution. Previously, someone handed us a sample, we tried to improve its quality. Now we're actually going to try to generate good approximations to a target directly. And one of the perhaps most popular approaches to this today is called Stein variational gradient descent, introduced by Liu and Wang. And the idea was to use one of these kernel Stein discrepancies to repeatedly update the locations of n sample points. So you'd start by drawing your points IID from, say, a Gaussian, and then jointly you would update their locations and using a rule that was derived from the KSD. The rule is pretty simple. It turns out it approximates a gradient step in KL divergence. It's also now known, as of last year, that it drives the KSD to 0 at a 1 over square root n rate. And it's also pretty simple to implement, although it's worth highlighting that each update costs n squared time, so that can be expensive. Now, just like before, you might be in a situation where the gradient evaluations inside of SVGD are expensive. And so you could also imagine substituting them with stochastic gradients. And it turns out if you use this stochastic SVGD, you get the same guarantees with many fewer likelihood evaluations. And here I've just shown you an example where you actually can achieve faster convergence, both in RMSE and log likelihood, by using just a fraction of the data points per sample point instead of all. Okay, now another approach to generating high-quality samples is called Stein points. And instead of starting with random draws from a distribution and moving the points around, we're simply going to greedily minimize the KSD. So you're going to find first the single point that offers the best approximation in KSD, and then iteratively you're going to add one point at a time, greedily improving that approximation. It turns out this also sends KSD to 0 at a certain rate, at square root log n over n. It's pretty simple to implement. It involves the quadratic time costs in early steps. One potential downside of this problem is that you have to consider all possible candidate points as the next candidate point, which itself is a difficult optimization problem. So there's a variant of Stein points that's called Stein points MCMC, which says that instead of looking over all of R to the D for your next sample point, you could instead generate a few iterates from a Markov chain and choose the best of those. And that's sufficient to get similar guarantees. And here I'm just showing you a little cartoon that illustrates some of the benefits of Stein point MCMC over even regular MCMC. What you find that due to the randomness of MCMC, you tend to get clumping and unnecessary clumping and some modes that are not quite well approximated, whereas with Stein point MCMC, points tend to repel one another, and so you get a better spread across your distribution. Okay, now so far I've mentioned a number of successful applications of Stein discrepancies, but I also want to highlight a number of opportunities for future development in hopes that anyone here might be interested in pursuing them. So the first is around improving scalability while maintaining convergence control. So we already saw a way to improve scalability by subsampling terms in the grad log P. That was the stochastic Stein discrepancies. But there's another source of expense in computing these kernel Stein discrepancies, which is the quadratic time cost of pairwise evaluations of your kernel. Because of that, there have been a few different proposals for improving this using using essentially linear time algorithms that approximate the kernel with a low-rank approximation. The first of these is called finite set Stein discrepancies, and the second is called random feature Stein discrepancies. Now, both of these seem to work quite well in practice, but there's still an open question: how well do they control convergence? This is a question that wasn't addressed at all for finite set Stein discrepancies and was only partially addressed for random feature Stein discrepancies. So I'd like to pose that to all of you as a question to solve. A second opportunity for future development is exploring the impact of the Stein operator choice. Now, an infinite number of operators T characterize P. We just picked an arbitrary one, the Langevin one. We literally picked it because it was the first diffusion we could think of, the first Markov process we could think of. But there are many other diffusions out there and many other Markov processes. And the natural question is, what is the right choice of T for my problem? And what is the right choice of T for my target distribution? How is the discrepancy impacted by changing that operator? And how do we pick the best operator in practice? Now, just to give you a hint, it turns out that I know for a fact that the Langevin operator is not the best operator for all targets. In particular, it's not a great choice for heavy-tailed distributions. We know that if grad log P is bounded, as it is for, say, a student's T distribution with heavy tails, and your kernels are the typical kernels that you would use, like a Gaussian or IMQ, then your KSD does not control convergence. Ever. Which is bad. But we've begun exploring alternative classes of operators that might be more suitable. So in particular, we've been exploring what we call diffusion Stein operators that use other diffusions in place of the Langevin diffusion. You can typically parameterize these in terms of an additional parameter, which is this matrix-valued function A. So it looks a lot like your original Langevin Stein discrepancy, except multiplied by this matrix-valued function. And it turns out that at least for some heavy-tailed distributions, you can design A to be an appropriate measure that controls convergence and non-convergence as you'd like. But I think the area is still significantly underexplored, and we still need more automated procedures for choosing these diffusion Stein operators. Another major problem that I think is common to probably all diffusion-based operators is that of isolated modes. The Langevin Stein operator is a local operator. It only looks at the gradient of your log density at the evaluation points. And that means it doesn't have a lot of information about, say, very isolated modes. A mixture of two Gaussians that are very separated looks very similar to a single Gaussian when you're only looking around one of the two modes. So this is a problem, and a problem that I think we really do want to face if we want to be able to use these tools more broadly. And there are a number of, I know, ongoing efforts to try to address this problem, but I think it's still a big open question. Okay, now you could also imagine tackling a number of new inferential tasks with these Stein discrepancy tools. So one early attempt at this was due to Wang and Liu. They developed what was called a Stein generative adversarial network in the days where generative adversarial networks, or GANs, were popular as generative models. So this is just a comparison of two different generative models from back in the day, 2016. On the left, you have a popular model called DC GAN, and on the right, a Stein GAN. And the idea here was that the Stein GAN was providing better quality, in this case, for generation of faces. Now, if anyone has been on the internet in the last few years, you've probably seen that we can generate faces that look much better than this today with alternative types of models, like diffusion models. And so the natural question is, can you adapt some of these Stein tools to improve those models as well? On the right, I'm showing you a different sort of application, which is to variational autoencoders. And here, we're using Stein discrepancies and Stein operators to generate what are called control variates to reduce the variance of stochastic gradient style training methods. And it turns out that Stein operators are quite useful for this sort of application and can lead to much faster training and better training quality by integrating them into the training procedure. Another direction is in parameter estimation. I find this one very interesting, but I think it's still underexplored. There's a tool called minimum Stein discrepancy estimation, which simply says, if you have a parametric model that is a sequence of distributions p, theta, indexed by some parameter theta, and you want to choose that theta, you could use a Stein discrepancy to choose it. Instead of optimizing your sample to approximate p, it's essentially optimizing your p to approximate your sample. Now, we do this sort of thing all the time, right, with maximum likelihood. But the problem is that maximum likelihood is actually difficult to do exactly when we don't know how to normalize our distribution. It's computationally intensive and typically involves some other approximation. Minimum Stein discrepancy estimation allows you to avoid the normalization constant and integration under p theta, which means you can carry this out even in these intractable, unnormalized models. Now, we've explored this only in simple models so far, but I think it has a lot of promise. And in particular, we've used it to design diffusion-based discrepancies that can deal with heavy tails and outliers using some of those diffusion Stein discrepancy tools that I mentioned earlier. Another application is to post-selection inference. So this is all about constrained targets. So far, I've been focused on unconstrained target distributions. I'm going to take a little dive into constrained target distributions now. It turns out that when you're doing inference after variable selection, so say you ran the lasso or variants like the randomized lasso, and you're interested in doing inference about the parameters that you've estimated, you end up with these constrained target distributions that describe the testing sets. And procedures like, so what you like to do in this case is actually sample from these constrained target distribution, which is a difficult thing to do. The constraint set is a little bit awkward. People have proposed using MCMC for this. Some have tried to use Stein variational gradient descent for this as well, but it's not really designed for a constrained target distribution. And so we've been designing different Stein discrepancies called mirror Stein discrepancies that are suitable for distributions on constraint sets. And on top of that, you can build what's called Stein variational mirror descent and mirrored SVG to actually do de novo sample generation on constrained sets. This, again, is still relatively new, still relatively unexplored, and I think there are lots of opportunities for future development. Another direction is non-convex optimization. We know how to do convex optimization well, but there are lots of problems where we have non-convex optimization, and we'd still like to get efficient algorithms. Here, the goal is to minimize a function f of x. To do this, we're going to think of it as a sampling problem. And we're going to try to sample from a series of distributions, which are called Gibbs distributions, which is just, I take my f of x, I take the exponential of the negative of f of x multiplied by an inverse temperature parameter. That's one of the Gibbs distributions. And I'm going to adjust this temperature parameter to converge more and more closely to around the modes of the distribution as the optimization algorithm progresses. And it turns out, by identifying appropriate diffusions using these same tools from diffusion Stein operators, you can also identify algorithms, sampling algorithms that would become good optimization algorithms. So here, we're going to use a Markov chain, which is a simple discretization of one of these diffusions parameterized by this matrix A that I mentioned earlier. You're going to take a step in the direction of the gradient multiplied by that matrix-valued function and with a little correction term. And you'll use that matrix-valued function, which I'll call a diffusion operator, to guide the noise in this in a Gaussian distribution. Now, it turns out that if your target distribution is distantly dissipative, which is basically has strongly log concave tails, and if you can choose the matrix function so that a of x times grad f of x is Lipschitz, so you basically want this to look like a Gaussian. You know, if f of x was just x squared, then you wouldn't need this matrix A. But for lots of targets, this matrix A helps you to make this target distribution look more like a Gaussian distribution. Well, okay, so if you can choose a of x times grad f of x such that you have that property, then your sample sequence running this Markov chain described above will actually converge to the target distribution. Sorry, converge to the optimizer of this function, the minimizer of this function. And I'll just give you a simple example of that. Here is a very simple function to optimize. The answer is 0, x equals 0. But it's non-convex. It has, it moves in a concave way away from the minimum, and it has these flat tails in the extremes. And you can imagine doing several different things to optimize this. You can imagine using gradient descent. That eventually will find the minimum, but very slowly. After 7,000 iterations, gradient descent only gets here. After 3,000, it's gotten about here. You can imagine using the Langevin algorithm to do that sort of amortized sampling that I described earlier. There, it actually ends up going off in the wrong direction because it's a poorly mixing process for this sort of target. But if instead you use this design diffusion, where you use this simple choice of A of x that makes the gradient look more like the gradient of a log Gaussian, then your optimization algorithm converges in just 15 steps. Finally, I wanted to mention the task of what we like to call distribution compression. That is, someone hands you a sample, and you know it's a good approximation of your target, but you'd like to compress it into a much smaller sample for downstream tasks that are very costly. For me, my interest in this task came about because of computational cardiologists who wanted to use samples of, who wanted to simulate a patient's heart in many different configurations, and they had too many different configurations to consider. And they asked, how can I reduce the total number of configurations while still capturing as much uncertainty about the original distribution as possible? In that case, each sample point represents an 1,000 CPU hour simulation, and so the fewer of those we can do, the better. One approach to this, which is pretty recent, is called Stein thinning. And the idea is that it has two steps. It's called Stein kernel thinning, and it has two steps. The first step is Stein thinning. You greedily minimize the KSD using your sample points as candidates. So I start with endpoints. I'm going to again pick out endpoints, and I can repeat points if I'd like, and I'm going to pick out those points to minimize the KSD as I go. It turns out that doing this original step, the Stein thinning step, has the benefit of also correcting for biases in your initial sample. And these biases can occur for all sorts of reasons. It could be due to off-target sampling. For instance, if you're using approximate MCMC, it could be due to tempering, which is sometimes done. Sometimes someone will approximate the wrong distribution just to get a Markov chain that mixes more quickly. It also can occur due to what's sometimes called burn-in. When you run your Markov chain, you have to start somewhere. And often that somewhere is an arbitrary place. In this case, my Markov chain started here, but the bulk of the posterior distribution is in this area. And so I'm left with this tail of points that really has nothing to do with the target distribution. It just has to do with my starting point. And if you were to run Stein thinning on this, it would actually throw away all of those points because they're not useful for approximating the target distribution, and it would just retain points in the high posterior density regions. Finally, after you do that Stein thinning, you compress that endpoint summary into a smaller square root endpoint summary with comparable KSD, and to do this, you can use a tool called kernel thinning that preserves a lot of the quality while greatly reducing your sample size. Okay, so that's about it. I just wanted to leave you with a summary of these opportunities for future development, in case this inspires any questions or inspires your future work. And I'll just say that I briefly mentioned control variates in there somewhere, and this has a long history. There's a long history of using Stein operators and Langevin operators to produce low Monte Carlo inducing control variates. And that's all I had to share today, so thank you for coming.
Thank you very much. We do have time for questions. This address is being recorded, as are others, for later enjoyment a few weeks hence. But that means that this only works if you step up to the microphones, which you find at the intersections of the aisles, as you're getting ready to ask a question. And I'll let Lester call on those who have questions.
Wonderful talk.
Thank you.
Do you have any maximum, like the maximum number of data points that, like, is there some limit that that you see?
Are you saying, like, is there a largest number of data points for which you could hope to, like, is it feasible to run the procedure, or
Yes.
is it?
Yeah.
Well, the thing I really like about the stochastic Stein discrepancies is that actually the more data points you have, the better, and that like you can get more gains in terms of computational speedups. And so when you're already taking an average over a large number of points, these guarantees actually improve when you have more candidate points to choose from. So, I mean, you can scale. The interesting thing about that is that even if you're just sampling 1 point per evaluation, you still get this property that you're converging with probability. You control convergence with probability 1. Although, if you want a stronger guarantee, like the Stein discrepancy curve traced out by your stochastic Stein discrepancy closely matches the curve traced out by your original discrepancy, then of course the more points you sample, the better. But for getting the same convergence control properties, even just sampling 1 point per sample point is sufficient. So I think that gives you a lot of scalability.
It looks like the most urgent questions have been asked. Those who are a little bit more shy than microphones allow have an opportunity to buttonhole the speaker right after this. Thank you all for coming, and thank you very much for an interesting talk.